Hi, my name is Skylar Mill, and today I will be presenting the final lab for Physics 2211, where we got to create our own adventure. I decided to analyze a falling slinky. This lab measures the slinky's motion from being expanded and then dropped from rest. The observed motion of this object will be measured and compared to a computational model to see how different forces affect an object's position. In order to look at motion, Newton's second law is needed. This law states that a force is applied on the system when there are interactions between objects. All these interactions can be added up to equal one net force, which can be measured as a change in momentum over a change in time. In this lab, the slinky is being dropped from rest, since the initial velocity of the object is 0 and then speeds up. This indicates that there is acceleration and a non-zero net force due to the momentum principle. One of the forces is gravity, or the force of Earth on the object. The gravitational force is proportional to the object's mass, and it has a specific constant of 9.8 meters per second squared. The atmosphere is made up of many particles, and these particles will have interactions with falling objects. These interactions result in drag force. The drag force is proportional to the square of the object's speed times the proportionality constant. The last force that needs to be considered is the slinky force. When the object is dropped, the tension is still the same in perspective from the bottom, so the slinky will not move until the top of the slinky has reached the bottom. Using tracker, the motion from the video of the object falling from rest was able to be measured. The center of mass of the object is indicated by the red dot in each frame as it moves in the negative y direction. The graph shows a relationship of the position versus time. The bottom of the slinky remains motionless as the tension force is equal to and opposite to the gravitational force, just as it was at rest. So the bottom of the slinky was chosen to analyze this type of motion. The mass of the slinky was 0.25 kilograms. In the glow scope code used to predict the motion of the falling slinky, the initial values from the observations are put in place, such as mass, position, velocity, gravitational acceleration constant, and the direction of the force. The B component for drag force was determined to be 2.6. In the first loop, time was indicated to represent when the bottom of the slinky was motionless. The forces interacting with the object during this time was just the gravitational tension forces, which are equal but opposite to each other. The velocity was updated from Newton's second law, and the update position formula was written in the code. In the second loop, the time was indicated to represent when the bottom of the slinky was in motion. The forces interacting with the object during this time were the gravitational and drag forces as indicated during the fundamental principles. The velocity and position update formulas were coded as well. The results show that the predicted and observed values are very similar except for a few discrepancies. This could be due to the fact that the slinky may have continued forces acting upon itself. It was originally analyzed that as the top of the slinky came in contact with the bottom of the slinky, it continued to fall as one, but there could still be tension and other factors contributing to the fall of the slinky.